This video is on vapor pressure, changes in state, and the Clausius-Clapeyron equation. So to start off with, we're going to talk about vapor pressure and the changes of state that happen. So when we look at a liquid to gas, we call that vaporization, and that's an endothermic process. Energy is coming from the surroundings to the system to put in energy to our molecules to give them enough energy to become a gas. So they go through the state change of vaporization. Here we have delta H vap, which is the enthalpy of vaporization. Also, we could refer to it as the heat of vaporization. If we're looking at water, the heat of vaporization of water is 40.7 kilojoules per mole. And this is a reflection on the liquid, in this case water, intermolecular forces, which we talked about previously. So the stronger the intermolecular forces, the higher the vapor pressure is going to be. If we were comparing that to acetone, acetone has a lower enthalpy of vaporization or heat of vaporization because it has weaker intermolecular forces between them. So looking at water, water is just hydrogens and oxygens, it's a very polar compound, whereas acetone is not nearly as polar, it's a larger molecule. And it still has the hydrogen bonds, but they're not nearly as strong as they would be in water. This is also why your body sweats to cool yourself. To sweat, you have water or sweat come out onto your skin, and then that water on your skin then vaporizes. And to do that, that requires energy. So it requires energy from you to vaporize, and that energy has to come from your body. So the heat goes then into the particles on your skin, the water particles on your skin, giving them energy to then evaporate. So lower energy particles will remain, which will feel cooler because they have less energy on your skin, and you'll feel cold. Then we'll talk about dynamic equilibrium. So dynamic equilibrium is something that needs to be discussed when talking about vapor pressure. So if we were to have a liquid in an open container, such as the Erlenmeyer flask here, all of my liquid would be open to the environment, and it would just come out. My liquid vapors would just come out of my container here. Now, if I had a closed container, my liquid vapors, so my liquid to vapor, those molecules would come out of the system, but then they would condense back down and go into the water. And so it would go back and forth, and so I'd have equal rates of evaporating and equal rates of condensing. So in just an open container, you would just have evaporation, but in a closed container, you'd have both vaporization and condensation. We say this creates a dynamic equilibrium, and equilibrium has to do with the rates. So the rate of vaporization, so of going out, is equal to the rate of condensation of them coming back in. And this is how we can make vapor pressure. So vapor pressure, we've talked about pressure before, which are collisions. So here they're collisions of vaporized particles with a container above the liquid. So right above the liquid, we're going to have different particles in the vapor phase, and they're colliding with a container, and that makes a pressure. We can have something called a volatile liquid, and this kind of liquid vaporizes easily and has a high vapor pressure. So these are things like gas and acetone. Right? If you were to squirt acetone onto the table, it would evaporate quickly. If you were taking off your nail polish and using a nail polish remover and you spill it, you just let it sit there and it evaporate by the time you go find the paper towels to clean it up. So we say that that's a volatile liquid. Not that it's going to explode, but that just vaporizes easily. So if we look at some vapor pressure and temperature graphs, we can see that vapor pressure, which are the lines here, increases exponentially with temperature. So on my y-axis, I have vapor pressure in atmospheres, and on my x-axis, I have temperature in degrees Celsius. As my temperature increases, as does my vapor pressure, and so it comes up in an exponential form. We can read across for acetone and water. At 1 atmosphere, acetone is going to boil, going from the liquid to gas phase, is going to boil at 56.2 degrees Celsius, whereas water is going to get to its vapor phase at 100 degrees Celsius. So we can see that, well, acetone will have a lower boiling point here at 1 atmosphere than water because it has weaker intermolecular forces, right? It requires less energy to get the molecules to move from one phase to the other. But we'll see that at all temperatures, acetone has a higher enthalpy of vaporization because of those weak intermolecular forces. So it has a lower heat of vaporization because of the weaker intermolecular forces. It has a higher vapor pressure because those molecules are more easily able to go into the vapor phase because of more volatile liquid. So more volatile liquids will have lower and weaker intermolecular forces. So these have weak intermolecular forces. Weak intermolecular forces cause low heats of vaporization and low boiling points because they don't require much energy to change phases. We can use math, a mathematical equation, to determine vaporization or vapor points and vapor pressure. So it's called the Clausius-Clapeyron Equation, and you get to use natural logs. Here, the natural log of vapor pressure 1 divided by vapor pressure 2 is equal to the heat of vaporization divided by R times the change in temperatures, but the inverse change in temperature. So 1 over T2 minus 1 over T1. It's important to note that R here, because we are dealing with energy, has to be the 8.3145 joules per mole Kelvin. Our temperature has to be in Kelvin because we're dealing with gases. And then VP stands for vapor pressure. So if we have 2 vapor pressures and 2 temperatures, then we can determine the heat of vaporization. Or if we know the heat of vaporization and 1 vapor pressure and 1 temperature, then we can calculate the vaporization or the vapor pressure at any temperature. So for example, if I have water at 25 degrees Celsius that has a vapor pressure of 27.95 torr, I want to calculate the new vapor pressure at 100 degrees Celsius. So I pull out my variables. I have an initial temperature of 25 degrees Celsius, which is 298 Kelvin. I have a vapor pressure that goes with that of 27.95 torr. I'm going to a new vapor pressure that I'm trying to calculate, and my new temperature is 100 degrees Celsius, which is 373 Kelvin. So using my equation, I have my natural log of my initial vapor pressure, my 27.95, divided by my new vapor pressure that I'm looking for, is equal to my heat of vaporization for water, which I know from before here is 40.7 kilojoules per mole, and my R value is in joules per mole, so I need to convert that. So that's 40,700 joules per mole. My R value is my 8.3145 times my temperature. So my second temperature I'm getting to is 373 Kelvin minus my initial temperature of 298 Kelvin. Now it doesn't really matter which one you choose as your T1, your vapor pressure 1, your vapor pressure 2, and your T2, as long as you're consistent in the formula. So if I have something in my natural log being divided by, I have to use that E button. And so when I do that, I have the E of the ln, and then I take, when I multiply all of this and divide all this together, I also have to take the E of this side. So when I do that, I get negative 3.30. When I take the E of my natural log of this, that cancels out the natural log. So I get 27.95 over my vapor pressure 2 is equal to, and then this has a numerical value of 0.0368. And then solving for V2, you cross multiply and divide. So my second vapor pressure is equal to 760 torr. Now I look at that value and it makes sense because I'm increasing my temperature, and I know that as I increase my temperature, my vapor pressure is also going to increase. So it makes sense that my vapor pressure is much higher, given the fact that my temperature is 4 times as high as when I started, and it's an exponential equation, so it's much more than 4 times higher. Another example is what temperature would produce a vapor pressure of 400 torr. So similar situation. I'm starting with my initial temperature as before for 298 Kelvin. I have my initial vapor pressure, same as before, of 27.95 torr. I want to know what's my new temperature if I get my gas to a vapor pressure of 400 torr. So I plug into my equation my natural log of my vapor pressure 1, which is my 27.95, divided by my vapor pressure 2, which is 400, equals my heat of vaporization, still the same as before, divided by my R value, times 1 over T2, which is what we're looking for, minus 1 over T1, which is our 298 Kelvin. So here I can just plug into my calculator my natural log 27.95 divided by 400, which is negative 2.66, equals, and then this divided by each other is 4,895, 1 over T2 minus 1 over T1. And then I can divide both sides by this, so I get negative 5.43 times 10 to the negative 4, which equals 1 over T2 minus 1 over, oops, this was your 298. So I plug in 1 divided by 298 in my calculator, and I add that to both sides, and when I do that, I get 0.00281 equals 1 over T2. So I cross multiply and divide, and I get 1 divided by this, which means that my T2 is equal to 356 Kelvin, which then you could convert into Celsius. You need to see that. Here you go. So to go back over what you couldn't see. So when I did my natural log, I get negative 2.66, and then I divided this here to get this number, and I kept this the same. Then I divided both sides by this to get my negative 5.43 times 10 to the negative 4 is equal to 1 over T2 minus 1 over 298. I did this in my calculator and added it to my other side. So I get 0.00281 equals 1 over T2. Cross multiply and divide, so 1 divided by this value gives me a new temperature to get my 400 torr to be 356 Kelvin.